Question 1. Describe the motion in each graph. So first of all, let's take a look at A. We're going to make 3 points. We're going to say that point A, right there is going to be point B, and right there is going to be point C. So between point A and point B, we are seeing position. So position is changing faster as the time is increasing. Okay, so position is changing, and it's non-uniform. Okay. In this case, since we have an increase in position with time, we would say therefore V is increasing, velocity is increasing, as the object accelerates. Okay, so we would say that acceleration is not 0. Between B and C, so between in this part right here, position is changing at a constant rate, meaning that V is not changing. So V is not changing. And since V is not changing, we would say that the acceleration is 0. It's going at a constant speed. In B, it's kind of the opposite. Position is changing more slowly as time increases. You can see that this curve is kind of the opposite of this curve here. Okay. Again, a linear change for a constant velocity would look something like that. Okay, we're actually slowing down. So we would say that in B, we are seeing a slowing down between this point and that point right there. Okay. Since we are slowing down, our V is decreasing, and therefore we are seeing an acceleration. Acceleration is not equal to 0. Since we're slowing down, it'd be like putting on the brakes. We would say that acceleration, therefore, must be a negative number or less than 0. Now, C is usually a little bit easier to look at if we think of it in terms of a car. So let's make a couple points. Again, we'll say this is point A right there. We'll say that is point B, C, D, and E, and that's going to make it a little easier to differentiate. So let's say between point A and point B. Between point A and point B, remember this is a velocity time graph, okay? We actually have an increase in velocity, okay? So the acceleration is going to be the slope. So between A and B, we would say that there is acceleration. So acceleration is occurring. The car is accelerating away from the origin. So we would say that accelerating away, okay, from the starting point. Between points B and C, the speed levels off and it starts to travel at a constant velocity. So you'd say that V is constant. And if V is constant, A is equal to 0. We have no acceleration. Between C and D, we can see that the car is slowing down. Okay, it would be like putting on the brakes. So the car is moving at a constant speed between B and C. From C to D, the car hits the brakes and slows down. Okay, so V is decreasing. Okay, therefore, A is less than 0. We have a negative acceleration. Okay. Eventually, it's going to come to a stop right where V equals 0. So it's like the car actually brakes. Then it's going to actually start moving backwards. So we're going to go from a forward motion between B and C. Okay. C at that point is going to slow down until it stops, and then we're going to start moving backwards until we hit D. So now we're at this point right here. So at point D, our velocity, excuse me, we start moving into the positive velocity again. So our car is moving backwards. Okay. It is going to start slowing down and eventually come to a stop. So maybe that wasn't clear. So between D and E, remember our car is traveling backwards. Okay. That backwards momentum is going to stop. Eventually at time E, so we say at E, velocity is 0. And we can see right there, velocity is 0. So our car has come to a complete stop. So to fully recap, from A to B, our car is accelerating away from the origin. Between B and C, it is traveling at a constant velocity. Between C and D, it's actually slowing down to the point where it stops right here. And then starts traveling backwards to D. And then between D and E, the car actually starts to slow down and eventually comes to a stop at E. State what each of the following represents. A, the slope of a tangent on a position-time graph of non-uniform motion. So there's my graph, position, time. There's my non-uniform motion, and there's my tangent. Not very straight, but there's my tangent. Okay. So the slope of the tangent is going to represent our instantaneous velocity at the particular point where the tangent hits the line. So at that instant, right there in time, that is going to be the instantaneous velocity. B, the slope of a line on a velocity time graph. Velocity, time, and we'll do some uniform motion. The slope, right there, is going to represent the acceleration of the object. C, the area under the line on an acceleration time graph. Acceleration time, the area underneath here is going to represent the change in velocity. Under what condition can an object have an eastward velocity and a westward acceleration at the same instant? Well, let's just say that an object, we'll call it VI, okay, is traveling at 30 meters per second, and we'll call this time 1. At time 2, the same object is traveling in the same direction at 15 meters per second. So we'll call this way east. Now you can see that our velocity has decreased. It's decreased from 30 to 15. And the reason it's decreased by 15 meters per second is that the vehicle, in this case, is slowing down. If a vehicle is slowing down, we say that it's accelerating in the westerly direction. So if an object is moving forward but slowing down, it is actually accelerating backwards. The world record for motorcycle acceleration occurred when it took a motorcycle only 6 seconds to go from rest to 281 kilometers per hour forward. Calculate the average acceleration in, I should say, A, kilometers per hour per second, and B, meters per second squared. So first of all, let's set up our positive directions. So we're going to call this forward, and we're going to call that positive. Second thing we always do is we always write down what we are given. We are told the time is 6 seconds. We're told VI is 0. We're told VF is 281 kilometers per hour forward. And we're looking for acceleration. Now we know our equation. Acceleration is going to equal to VF minus VI over t. We plug our numbers in. We get a VF of 281 minus 0 divided by 6. And our acceleration is 47 kilometers per hour per second. And this needs a direction since this is a vector quantity, so we would say in the forward direction. B states they want that number in meters per second. So we say 47 kilometers per hour second, okay, times 1 hour every 3,600 seconds times 1,000 meters every 1 kilometer. So now what can we cross? We can cross out kilometers. We can cross out hours. We do the math, and we end up with 13 meters per second squared forward. Okay, so we have an answer there, and we have an answer there. One of the world's fastest roller coasters has a velocity of 8 kilometers per hour forward. So we would say that VI equals 8.0 kilometers per hour forward. It's always a good idea to write these things down as you're reading it. As it starts its descent on the first hill. Determine the coaster's maximum velocity. So VF, that's a question. At the base of the hill, assuming the average acceleration is 35.3 kilometers per hour per second forward. And time is 4.3 seconds. Now let's again assign forward as that way. And we'll call that positive just to make our life easier. We know our equation, A equals VF minus VI over T. What we are looking for is VF, so we need to isolate VF. We're going to multiply both sides by T, so we get AT equals VF minus VI. You can add VI to both sides, bringing VI over to the left side of the equation. So what you end up with is AT plus VI equals VF. Now we plug some numbers in. We know our acceleration is 35.3. We know our time is 4.3 seconds. We know our initial velocity is 8 meters per second, and that's all going to equal VF. Now when you do your calculations, VF comes out to 159.8 kilometers per hour. We need 2 sig digs in this question because of the 8 over here. So our answer becomes 160 kilometers per hour forward. With what initial velocity, so our question is asking for VI, that's our question, must a badminton birdie be traveling if in the next 0.8 seconds, so time equals 0.8 seconds, its velocity is reduced to 37 meters per second, so VF is 37 meters per second forward. Assuming that the air resistance causes an average acceleration of negative 46 meters per second squared forward. Another way of writing that would of course simply be 46 meters per second squared backwards. In which case you would drop the positive because we are going to assign that way to be forward, and we're going to call that positive. So again, let's write out our equation. A equals VF minus VI over T. We are looking for VI in this case. So let's rearrange. Again, we're going to multiply both sides by T, so we're left with AT equals VF minus VI. Now there's certainly faster ways of doing this, but let's just swap the VI over to the other side, shall we? So we're going to take this, we're going to move it over here, and we're going to take this, and we're going to move it over there. When you change sides, you need to change signs. Okay, so we'll be left with positive VI equals VF minus AT. Now we can plug in some numbers. We know VF is 37 minus our acceleration is negative 46 because it's going backwards. We already assigned forward as positive right there. Okay, and then we're going to multiply that by the time, which is 0.8 seconds. When you do the math, you get 74 meters per second forward. During part of a blast-off of a spaceship shuttle, the velocity of the shuttle changes from 125 meters per second up to 344 meters per second up in 2.3 seconds. So first of all, let's assign up as positive. Okay, we know that it changes, so VI equals 125 meters per second up. VF equals 344 meters per second up. And we know time is 2.3 seconds. Determine the average acceleration experienced by the astronauts on board during this time trial. So that would be A, that would be B. So A is the question. So again, A equals VF minus VI over T. We plug our numbers in, you get 344 minus 125 all over 2.3. And you get an acceleration excuse me, of 95.2 meters per second squared up. This rate of acceleration would be dangerous if the astronauts were standing or even sitting vertically in the shuttle. What is this danger? So what is this danger? Well, if you are accelerating too quickly, the blood rushes. So I'll just do one of my famous drawings here. Okay, so there's blood in your brain, okay, blood everywhere. But if you accelerate really, really quickly, that blood, due to inertia, stays where it was, or it tries to stay where it was. So what happens is that blood pools in your feet. Okay, it doesn't actually leave your body like my drawing kind of looks like, but what you end up with is a lot of blood in your legs, okay, and less as you move up. The less blood you have in your brain can cause things like blackouts, which would be very dangerous if you're trying to fly a spaceship. In an acceleration test for a sports car, two markers, 0.3 kilometers apart, so distance equals 0.3 kilometers, which is going to equal 300 meters. We're set up along a road. The car passed the first marker with velocity of 5 meters per second, so we say VI equals 5 meters per second east, and passes the second marker with a velocity of 33 meters per second east, so VF is 33 meters per second east. Calculate the car's acceleration between the two markers, so A equals question mark. So the first thing we need to do is, again, we need to assign a direction, so we'll call that east, and we'll say that is positive. The second thing we need to do is identify which equation we are going to use. Well, the only equation that really works is VF squared equals VI squared plus 2AD. Okay, A is what we are looking for, so we're going to need to solve for A. So let's put some numbers in first. So VF is 33, so 33 squared equals 5 squared plus 2 times A times 300. So now you know why we changed to 300 meters, because all our dealings are in meters per second, and so on. Okay, so when you do a little bit of math and a little rearranging, you end up with 1089 minus 25 equals 600A. Okay? We are then going to divide both sides by 600. Okay? And what we are going to end up with is A equals 1.8 meters per second squared east. A baseball traveling at 26 meters per second forward, so we say VI is equal to 26 meters per second forward, strikes a catcher's mitt and comes to a stop while moving 9 centimeters forward. So the ball's actually going to move the catcher's mitt in the direction of the initial motion. So we'll say displacement is going to equal 9 centimeters, which is going to equal to 0.09 meters, since all our units are in meters. Calculate the average acceleration of the ball as it is stopping. Since it's stopping, VF is, of course, 0. So again, let's assign that to be forward, that to be positive. Now, again, you need to find the equation you need to use. So again, we can use, just like last question, VF squared equals VI squared plus 2AD. We plug our numbers in. VF is 0. VI is 26, so 26 squared, plus 2 times A is what we're looking for, times 0.09. Once you've done a little bit of rearranging, you end up with an acceleration of negative 3,755.5. We need 2 sig digs, so we get 3.8 meters per second squared backwards. Now, why is it backwards? Well, the negative, okay, forward is positive, therefore negative has to be backwards. A plane traveling at 52 meters per second west, so VI is 52 meters per second west. Down runway begins accelerating uniformly at 2.8 meters per second squared west. Since we are talking about west, let's say that's west, and we'll call west positive to make our life a lot easier. A says, what is the plane's velocity? So VF is the question, when t equals 5 seconds. So again, we got to figure out what equation we want to use. Let's use our basic A equals VF minus VI over t. 2.8 equals VF minus 52 divided by 5. We do a little bit of rearranging, and we get VF equal to 66 meters per second west. B says, how far has it traveled? So D is the question. During this 5-second interval, t equals 5. Now we also have VF. We just figured VF out. VF is 66 meters per second west. So let's use the equation that makes life easier for us. Let's say VF squared equals VI squared plus 2AD. In this question, D is what we're looking for, so we need to solve for D. Let's plug in some numbers. Okay, we know VF is 66 squared. VI is 52. We'll square that. 2 times our acceleration we know is 2.8, and of course we are looking for D. We do some rearranging, and we get D equal to 295 meters. We need 2 sig digs, therefore 3.0 times 10 to the 2 meters. And since we're talking about displacement, we say west. A skier starting from rest accelerates uniformly downhill at 1.8 meters per second squared. So we'll say A is 1.8 meters per second squared. And since we're going downhill, let's just say, we'll call that forward. Okay, we'll assign forward as being positive. How long does it take? So how long? So T is the question. The skier to reach a point 95 meters forward. So D is 95 meters forward from the starting position. Okay. Since we start from rest, we also know that VI is equal to 0. As always, we need to figure out our equation. So let's use D equals VIT plus 1/2 AT squared. Now, what we're looking for is T, and T. Now, this question would be quite difficult, if VI wasn't equal to 0, but thankfully it is. So let's put the numbers in. 95 equals 0, so we don't need to worry about that part of the equation at all. Plus 1/2, A is 1.8, and of course T is our question. We do some rearranging. We get T squared equals 105.6 seconds. Therefore, T equals 10.3 seconds. We need 2 sig digs, so now our final therefore time equals 1.0 times 10 to the 2, times 10 to the 1. 10 to the 1 seconds. For a certain motorcycle, the magnitude of the braking acceleration is 4 Gs. This should actually look more like magnitude, 4 Gs. So we'll say acceleration is 4 Gs. Now, 4 Gs simply means 4 times the acceleration of gravity, which is 9.8. 4 times 9.8 is 39.2 meters per second squared. Okay. Next thing we have, if the bike is traveling at 30, so we have VI is 32 meters per second south. Since we're talking about braking, we know now that this is going to be north because it's going to work in opposition to motion. A says, how long does it take to stop? Well, then that for it is t is equal to 0. Since we're looking for it to stop, we know VF is also equal to 0. Excuse me. We know t is the question. And VF is equal to 0. So we're getting a little ahead of myself here. So we need an equation. Okay. So let's use, again, our basic A equals VF minus VI over t. And t is what we're looking for. We do some rearranging. We know that now t is going to equal to VF minus VI over A. You plug the numbers in. VF was 0. 0 minus 32 over our acceleration of 39.2. And we end up getting t is equal to 0.82 seconds. So one slight addition, that is a negative acceleration since it's moving in opposition to motion. And that will give us a positive time value. A car traveling along a highway must uniformly reduce its velocity to 12 meters per second north in 3 seconds. So VF, that's the goal, is going to be 12 meters per second north. Time is 3 seconds. Let's assign north to be positive. If the displacement traveled, so D is 58 meters north during that time, what is the car's A, average acceleration, and B, initial velocity? So let's start with A. What is the car's acceleration? Well, let's use an equation. Let's use D equals VFT minus 1/2 AT squared. And we're going to plug in some numbers. We have 58. We have a VF of 12, a time of 3, minus 1/2 A, and then 3 squared. We do some rearranging. A equals negative 4.89 meters per second squared. Now, since it's negative 4.89, we can therefore state, and since we need 2 sig digs, the acceleration is actually 4.9 meters per second squared south, because it's in opposition to motion. B asks us for VI. In this case, let's use the equation A equals VA equals, ahead of myself, VF minus VI over T. Okay. Plug some numbers in. Now, for acceleration, we need to use the negative, okay, because it's going to be opposite to the motion. So we'll say negative 4.89. Now, it's important to note we use one extra sig dig, okay, than our previous rounded answer. This is to avoid any kind of rounding errors. And that's going to equal to 12 minus VI over 3. Once you've done a little bit of rearranging, you get VI equal to 27 meters per second. Now, it's a positive number, therefore we know that VI must be in the northern direction. If you've used your signs properly, you'll always come out with the proper direction.